runtime has a lot of knowledge that probably they can give us insight to design the future architecture. And we call runtime-aware architecture. You can change the interconnection network. You can change the protocol. You can change many things, okay? And now I think that we need to apply the knowledge we can get at runtime with techniques coming from artificial intelligence to design better architecture. In this way, we have here Professor Daniel Jimenez, who was pioneer, proposing many years ago the use of the perceptron for branch predictor, and now you have a very good paper how to use dynamically information we get at the runtime to do a better optimization of the given catch. So I think that using the high number of data we can get at runtime and multi-core, and using in parallel techniques coming from the artificial intelligence, we can get more knowledge, we can organize better, use better in order to reduce power the current hardware, and the most important thing is we can propose different kind of processor for the future. The best thing I finish is just would be to have some kind of reconfigurability, but for the moment the PCA are not ready just to be changes on the fly. But that would be probably the best way to reduce dramatically the power we need to run application.
Good. Let me now address Paul. Yes, sorry.
I'll just throw in a couple of quick comments. One is an anecdote about special purpose computers. So the Anton, fantastic design, great system. Many people think of that as only a hardware design effort. Well, John Salmon, who used to be in my group at Caltech, has been working for D.E. Shaw Research for the last 10 years. And I met with him a few years ago. The operating system had to be done from scratch for the Anton, and it was as big an effort in terms of human effort as the hardware. So that's only one data point, but we shouldn't think of these specialized architectures, even for a given application, to be the end of the story in terms of the hardware design. So if you want to move on to a different topic.
Yeah.
Yeah.
Actually, you make a very good transition since it's about resources also. And when we see the multitude of new things that are coming up, architectures, software, compilers, et cetera, et cetera. So what about the skills? How do we prepare our people to be able to address all those? So one thing is science, one thing is academia, one thing is, of course, the research part. The other thing is all the users and how we train them to use these technologies and the new tools. So are we well equipped? Are we missing fundamental elements where we should all work together or separately? I don't know. What would be your approach?
In terms of enabling people to use the systems?
In terms of both those who develop and those who use, both.
Right, certainly what we're trying to do, and I don't think we're unique in this by any means, is to, we hope to have a software stack that's suitable for Exascale, but also suitable for people who don't need Exascale, but who perhaps in the future will. The idea being that the software stack would be usable by people who only need what we would call today powerful clusters. It would be usable by people in industry who usually have less expertise and less people, as well as for the people that are, the ninjas and can program any system. So that's one approach, to have the software. Certainly training is another that's obvious and very powerful. 5 years ago, I started a 2-week training program that was modeled actually on something that I saw Fabrizio Gagliardi do for grids 15, 20 years ago. But I did it for extreme scale computing, and that seems to be a useful way as well. I think training has a huge leverage because there are a lot of smart people, and in just a few weeks or sometimes a few days, they can learn that there exist algorithms, that there exist tools that we're not aware of. Our user community is very splintered, which is normal because they're geophysicists, they're chemists, they're psychologists that use computers, so they won't be up to date. So to the extent that we can disseminate information and give hands-on training, I think that also goes a long way. But the software, a little bit like what Allison said, people come to her with a new hardware design, and say, who's interested in it? When people come to me with a new software tool idea, I say, tell me 3 things that you know it's good for, not just that it may someday be useful. So it has to be useful.
You are in direct contact on that with people who have the problems.
I think there's several things, which make it much more complicated to recruit people. I think the first thing I've noticed is that certainly in our line of work, and I think increasingly it's going to be true as people work in teams and are combining expertise, is you need to hire people who have very good communication skills, who can listen to their colleagues, who can work interactively. So you can't just take people who are the top students in their class because they're very clever. If they can't work with other people, they can't communicate their ideas, then they're not going to be part of a successful team moving forward. Also in our line of work, we have to put a lot of effort into things like user interfaces. One of the things we've had to develop to get chemists using the high-performance computing is to set up something so they push a button, they can run their jobs from an iPad. So command line Linux is not something for everybody, no matter how good the software stack is. We need to make it easy to use. And I think the other area I've noticed where we particularly will have problems in training up people is in data science. So I think there's 2 problems there. Firstly, the Googles and people like that can hire the best graduates much more easily than centers like ours or academic centers. But also the old traditional model whereby you have a professor with 30 years experience who can impart that knowledge to students doesn't work on something like data science where the technology, the techniques, the algorithms are changing very fast and where a lot of the innovation comes from very young people. So we need to change some of the models, we need to introduce more collaborative ways of working, and we need to be much more imaginative in how we train people.
Yeah, so that's a big issue. The shortage of the talents is a big issue in China. Yeah, it's we have a lot of people, but for the talents, it's still always in shortage. And we just had some cases in the Guangzhou Supercomputing Center. Some experienced staff quit from the center because of the high salary offered by the BAT, the Baidu, Alibaba, and Tencent, such those companies. So that there is a competition between the academia and the industry. And I think we should address that issue from 2 aspects. One is try to hide the complexity from the end users. That means to develop the framework, develop the library, right, develop the tools so that it becomes easier to use those Exascale systems. Another way is to train people. For the undergraduate program, we think that there should be introduction courses for the computation for every students in the university. And also we are trying to design a curriculum combining the computing and also the domain knowledge. So that means those kind of people will have very good job after their graduation. And we also design a project and our key project called the HPC Education Practice Platform. That means to offer the content and also to offer the free hours to the undergraduate and graduate students. So they are supposed to offer 20 million hours to the students every year. So that's kind of current activities.
So I'd like to agree to everything that's been said. Yes, training is important. For example, Tsubame is like everybody's supercomputer. We let undergraduates use them, and so forth. So all these are very important points. One thing to add my little 2 cents. So I think this is very particularly acute in Japan. Maybe not so much in the U.S. or to less degree in Europe. So whenever you have a discipline like chemistry, whatever. And people do simulation. So there's like the top tier people who do exascale stuff, for example. Right? They scale to their code. They're proud of scaling their code to 1 million cores or something. But there's a vast majority of people who don't exploit that scale. They still do lots of simulation, but they may use fairly common codes, like, even at my center, still a lot of people use Gaussian, which doesn't scale. Now, but then you ask the question, okay, is this good? Because as Yupei mentioned, we get a lot of brain drain from other parts of IT and other parts of industry that offer higher salaries. And the reason one of the reasons they could do that, and one of the reasons, for example, like AI has proliferated so much, is they all basically use the same library, same frameworks. A lot of people don't write frameworks. Most people in AI use the frameworks. They may be like 5 or 10 of them. There are like 10 of them, and they may be one may be better than the other for certain purposes, but at least people don't start from scratch. But a lot of people in the HPC arena and the high end, especially like those in Japan, have this Galapagos attitude. They don't use other people's code, and they're very proud of this. And I find it to be very unproductive, right? So why aren't we forcing people for two reasons? One is, of course, that's extra work for them, and also a lot of their scientific results or even the algorithms themselves do not proliferate because they use very specialized code that's not supported by the industry, or at least by the community. So I think there needs to be much more proactive effort to utilize very well, what's been practiced on the domains, basically software engineering disciplines, where we leverage each other's frameworks as much as possible, and only let the domain scientists excel in their own specialized coding or specialized algorithms, but based on existing platforms. I think that's really necessary as we move on. Good. Don't let domain scientists develop from scratch unless there's a very, very good reason to.
Very good. Let's turn now into the audience. I think we have our entering little by little in the last quarter of this panel. So let's get 1-2 questions from the audience. Yes, please.
Hello, I'm Adriana Wild from the University of Southampton. My question to the panelists about attention that I see from your various interventions there. There seems to be one end wanting to make a high performance computing simpler for the typical scientist that is not a computer scientist. So the interface is, the complexity is obscured. They submit their jobs and they do their big science, and you submit that for them. But on the other hand, it seems that the major improvements are in minimizing that overhead communication. So you really can't obscure that complexity. So clearly you cannot do that without sacrificing the others. So what are your opinions on how do you think that tension can be resolved? Thank you.
Let's take also the next question so that we can take that both together. So here in front, please.
Well, may I address the question that was posed? Take both of them.
I would like to ask about the efficiency. Now, I would not embarrass you to ask about the real application performance efficiency with respect to the peak. This is an important question if you can comment on that. It's a pain all the time for the years. But another one is the efficiency of running the machine with respect to electricity and energy it consumes. And then if you can reflect on the future designs to understand if you take the same program, is it going to be less expensive to run it on the new machines than running it on current generation? How do you see this progression and evolution of that kind of energy efficiency?
Thank you. Let's start with a question on the complexity and the interfacing aspects, etc. Who would like to address that? Paul.
So I think the approach, which is not a new one, is to foster the use of libraries. So for example, in the Exascale computing project in the United States, where I said we have 66 software projects, well, one of them is MPI. And why is that? Because people use MPI, but what are we doing in this project is under the covers, if you will, underneath, improving MPI so that it can do a much better job of doing memory access when something is within a node, or doing an actual data transfer across nodes when that's where the data are, so that the application user doesn't have to worry about that as much, or perhaps at all. In mathematical algorithms, of course, we've always done that. So the algorithms have to be good, they have to be implemented well, they have to be available on the systems, otherwise people will say, well, I can't use it because it's only available on this system. So libraries, I think, are a big way, it's not a new way, but a very effective way of enabling the users from not having to learn every quirk of every vector unit, every memory unit. Is it shared cache? How much is it shared? And in which way is it shared? I think that was part of the complexity that you were getting to. It won't solve all the problems, but it can go a very long ways.
Good. Any additional aspects?
Yeah, I just, years ago, one of my colleagues said, it seems like you should be writing programs to write programs rather than just directly writing them yourselves. And I think that I agree, libraries are an important part of the solution, but I also think that even if it's not a general purpose compiler, that we should be thinking about tools that also generate code, JITs and things like this. I mean, and just also I'm going to tie this back a little bit to the previous discussion about attracting talent and workforce development and so on. I think the one thing that we have going for us in these scientific facilities and organizations is working on the most exciting science problems, which is one of the ways that we will also attract computer scientists, but we also need to let the computer scientists work on exciting problems, some of which will be high risk, and hopefully have high payoff for the broader scientific community. So I think that it is important that we look at things that will, perhaps translate and things like that into very efficient code.
Let's limit our reply.
Yeah, I'll make it very short. I think the other thing which is happening in the UK that you're probably aware of is there's a big movement towards research software engineering and professionalizing the development of research software. So we may not be able to reduce the complexity, but by having cohorts of people who are trained in software engineering and see that as being an important part of their profession rather than just being a scientist who writes code, being a professional research software developer. I think that's one of the other developments that's going to be very important.
Can I just really quickly follow? I completely agree with that, and I think it's really important that we separate software engineers from computer science researchers, because they're not,
Good. Let's move to the second, to the power efficiency aspects.
No, just
you would like
comment.
still to add something?
Can I comment? I mean, life is very difficult. Like, we would like to have a very nice interface, simple, to use very complicated hardware resources. This is not as possible. As I say, a big advantage is just to decouple the way the person who are designing the algorithm and the hardware, giving the power to the runtime. But as Professor Jesus Labarta say, the big revolution would be to change the mentality of the programmers. They are thinking in a very short things. Okay, just I will do that and I will finish that. No, try to think global and specify local. Trading latency, who has been the big problem at any level for bandwidth.
Good, efficiency. Power.
I would like to emphasize the usage of tools. So we think that there are three set of default tools. One is we already know the debugger, it's for correctness. The second one is for the performance tuning. That's for the efficiency of the software. And third one is for energy efficiency. That's power consumption tuning. So just like the performance tuning, we will tune the code to find the most power consumption part of the code, probably to rewrite the code with some direction of the tools. So that's, I think the tools are very important to increase the efficiency. But also, I think a comprehensive or holistic approach is important. That means we not only emphasize the programming part, but we have to study from the very beginning the mathematical method, the algorithm from the mathematics, and also the architecture oriented optimization of the algorithm. So for those comprehensive efforts and plus the runtime optimizations, I think that's a way to improve the efficiency of the software.
Satoshi?
Okay, so efficiency. Well, I know very much well about efficiency. So firstly, I think this, I used to say that this classical notion of double precision efficiency of the machine with respect to the real code, efficient real code versus this peak double precision efficiency is totally stupid. Has no sense at all, because firstly, if you look at any application, there is almost no application that exercise dense double linear algebra. Almost zero. Almost zero. The only thing I can think of is maybe quantum chemistry. Then you can fake that using multiple. You can change several single precision numbers to get almost the same effect. Anything else? Of course, you still need some double precision, like for sparse codes, like any sort of multi-grid conjugate gradient. All these require double precision, but very, very few, because it's memory bound. But in the past, what people have done is to might as well pack double precision anyhow, because you might use it for like quantum chemistry. And then there are really no other competition, because if you put more cores in, that's gonna that's harder, and that'll blow your power budget and so forth. Now, so all this kind of I was on a crusade saying double precision is not very important, but might as well put it in, and to kind of get high impact scores for bragging rights. But now we have a competitor. Now things have changed in the past few years. Now we have a competitor in terms, and this is a very important lesson. Now we have a competitor called machine learning, or CC, and the competitor says that we can put more single precision or low precision arithmetic units in, and actually the applications can use them. So take a very concrete example. Okay, you take this. So Kathy has a whole bunch of Knights Landing processor at her center. Now Intel has this new Knights Mill processor, which basically halves the floating point unit, double precision floating point unit. So her peak performance will go down by half, but it has twice the number of single precision floating point units and some integer acceleration. So her single precision peak number will double. So which is a better processor for real HPC app? Now I would say contest that it's the latter. So the only thing Kathy will lose by exchanging all the Knights Landing by Knights Mill processor is the bragging rights for Limpact. For things like the machine learning stuff that she had presented, the 15 petaflops stuff, that will probably double, right? Real application going from 15 petaflops to 30 petaflops, and that's real performance. So this kind of teaches a lesson. So we really should be cognizant of the investment we make with respect to chip real estate, to interconnect and everything. Because right now because of the power restriction, also for cost restrictions, that we are really getting to the realm, and this is, by the way, caused by this end of Moore's law, that the applications are starting to really fight for real estate and share of the machine resource in a much more aggressive way than in the past. So we should be cognizant of real efficiency of real applications. And power is one of them, but other things are as important as well. So this is really a lesson. Things are really changing. We should really be cognizant of efficiency and not worry about, but still not worry about double precision dense linear algebra.
Good.
Yeah.
Real,
Thank you. Just
yes. Real situation. When we installed the Mare Nostrum 4 in 04, and now installed the Mare Nostrum 1, and now the Mare Nostrum 4, this one is 300 times faster than the first one, just spending 3 times the power electricity. But the efficiency of the new machine is lower than the efficiency of the first Mare Nostrum. There is still plenty of room in order to get the resources the processor have to use efficiently. And this was my first point in my presentation. Real performance is the big challenge, one of the big challenges for the future Exascale.
Thank you, Matteo. We have 3 minutes left. I would like to get one message that you would like to convey to the room, especially to our young people, young researchers who are here, about the future. So starting by Kathy, what would be your main message for them?
I think there's lots of really interesting computer science challenges, as you've heard here. So hopefully, and also interesting science problems if you're interested in working with scientists.
From a computer architecture perspective, computer architecture is a really challenging, interesting field to be in right now. Much more interesting than it was when I got my PhD 30 years ago.
Teamwork is going to be key to solving the problems in the future, so I think you should get used to working with lots of different people from different disciplines, and that's the way we're going to achieve major breakthroughs.
Though the job developing Exascale is tough, but from the historical point of view, after 10 years we reviewed today, it's a trivial task. So I think we will emphasize the process of addressing those grand challenges and also looking for international cooperations to do something jointly.
I think Kathy's slide kind of said, with the couches, you can synonymize with like dark ages of computer architecture, for example, because, it was Moore's Law. Now, I think it's a time of renaissance in a sense, because now the old disciplines are fading away. So it's great to be in computing for the young generations. Don't get bound by old aesthetics, old rules, and try to be innovative. I think that's my, because it's renaissance.
So I would have said what Alison said, but since she said it, let me add that I feel I've had an extremely exciting career because I've worked from, in some cases, the math side, working with applications, in other cases, working from the application side with computer scientists. So I encourage people to get into what I will call scientific computing or computational science, whether you're a software engineer, computer scientist, applied mathematician, working with other people, you always have new frontiers, and also computing is becoming more important to society and can make great contributions to society. So it's also a very worthwhile thing on the ethical basis.
To the young people, I would say I would like to have your age, to spend my life doing research, not just in hardware as I did, but in the collaboration between the hardware and the software. Is the future, okay? If I can spend 30 seconds more, continue, I would like, because when I say at the beginning that we are going to start a European initiative, it's called EPI, European Process Initiative, it doesn't mean that, obviously, that we are not going to continue collaborating with Intel, IBM, NVIDIA. In fact, this is a small part, it's a specific European project, but we have a huge ecosystem with a lot of money, theoretically. I trust always in you, yes. Where we are going to have pre-exascale, exascale demonstrator, where, obviously, technology from outside will be necessary, okay? So please try to collaborate with us, with Europe, and then at the hardware level, I think it's a very good opportunity, as Kathy said, to establish a real collaboration worldwide in the design also of the hardware as we do, and the hardware as we do in the software. So thank you.
Thank you. I enjoyed very much chairing this panel, ladies, gentlemen, so it was a real pleasure. I hope you enjoyed it as much as I, so.
Yeah, okay, so after this fantastic panel following the really illuminated presentation by Kathy, I really want to thank the panel and Thomas. Well, we also have a little sign of appreciation